One other question I forgot to mention at the end of the last video, we just saw that the integral is acting as a lower bound on the sum. It would be also nice to get an upper bound on the sum, because if you have an upper and lower bound, you know how far off you might possibly be. So we'll keep that in mind. It's often a good idea to graph stuff. So let's say what's kind of going on with the sequence here. So here's a sub n, so it's the sequence, not the series. And we're just saying add this y value and that y value and that y value and that y value, etc. So we can kind of think of these each as a little stick, and we're saying add up the lengths of those sticks. So that's what's going on with the sum, with the sequence, and turning it into a sum. What's going on with the integral? With the integral, we've got the same points here because we're using the same function a sub n, but then we're taking the area underneath it. So somehow we were comparing a sum of stick lengths to an area, which doesn't exactly make sense. Can we reinterpret one as the other? Let's think about that. So let's do the same graph again. So we'll have that, 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 that. And let's think about the integral. I'm going to draw a nice continuous curve here through those points. Is there a way we can interpret those points as the stick lengths as areas? Well, usually to do an area, we do a length times a width. And if I did times a width of 1, I would get an area of a rectangle whose area number would be the same as the length of the stick on this side, because it's that stick times 1. So if I could draw something like this, then I've turned this stick length, a sub 1, into an area, because I've got delta x equals 1. And then I could do the same thing over here. Delta x is equal to 1 there as well. And the same thing over here. Delta x is equal to 1 there. So I'm turning each of these stick lengths into an area that is the same number and then adding them up. So have we ever done this before, taking a smooth curve and kind of saying, hey, there's kind of boxes going on here? This looks like the left-hand method for an integral, right? So in some sense, the integral is approximated by that sum, and that sum is the left-hand method. And is it clear now why the integral is less than the summation? So we could say the summation is greater than the integral, since the smooth curve is always less than or equal to the points of the sequence. And their box tops. So I think we've mostly answered our first question of why are we seeing what we saw in the spreadsheet. Another question is, can we trust it? Another way to ask, can we trust it, is what could go wrong? So let's write that down. What could go wrong? It's more fun to ask, what could possibly go wrong? Well, will we always have this smooth curve underneath the box tops here? What could happen to make that not work? Well, if one of these heights was negative, then things would get complicated. If a sub n was less than 0, maybe it would all work out, but we'd have to think really hard about it. Another one would be if the red curve started increasing, then this left-hand method, the box tops would go underneath the red curve. So we need that smooth curve and the a sub n values. If it was increasing, that would be bad. But as long as the red curve, the a sub n values, are decreasing and positive, we should be good. So let's write that down. there's an exception to the what we need here, and that is if we had a sub n maybe decreasing and then increasing for a while and eventually going negative or something, but eventually it kind of behaved nicely. It was steadily decreasing and positive. We could say right here, from there on it's good. And back here, we would lose the ability to say one is definitely greater than the other, but at least from this hard cutoff onward, we're fine. So we could say here, as long as this is ultimately true, that is, for some cutoff onward, a sub n is greater than 0 and a sub n is decreasing, then the sum and the integral should have this comparison from then on if we ignore all the initial stuff. And all that initial stuff is just finite numbers, and you could do the sum and the integral separately and compare them. You wouldn't have to be worrying about, shall I sum to infinity or not? So in the next video, we'll write this more formally.